everyone, my name is Khalish Zafran, and today I'm going to demonstrate how to solve questions for the trial question KMPk set B for the year 2022 and 2023. So let's go to question number 3. So the question here says that there are 3 possible resonance structures for the laughing gas nitrous oxide N2O. Alright, so we know there are going to be 3 resonance structures. So the first question is draw all the possible structures of gas nitrous oxide. So it's already stated that there are going to be 3. So that's how much we're going to draw. So we're going to draw 3 possible Lewis structures for nitrous oxide. Okay, so if you want to draw, if you want to draw Lewis structure, you of course have to start with the total valence electron. Nitrogen has 5 valence electrons, and from the molecule it has 2, so 5 times 2 is 10. And oxygen has 6 valence electrons, and from the molecule it has 1, so 6 times 1 is 6. So 10 plus 6 is 16, so there's going to be 16 total valence electrons in that structure. So I'm going to start here first. So O and N. Again, 16. So 16, there's 2 lines, so 2 times 2 lines, so 1 line represents 2 electrons, so 2 lines is 4 electrons, so minus 4. We get 12, so 12, they're going to be 1, 2, 3, 4, 5, 6 here, 1, 2, 3, 4, 5, 6 here. But as you can see, so 12 minus by 12, 6 to 0, but we're not finished yet because we have to recheck. As you can see here, for the oxygen, it already has octet valence electrons 2, 4, 6, 8, and for this nitrogen it also has octet 2, 4, 6, 8. But if you look closely, the central atom, which is the nitrogen, only has 2 valence electron, and it has not reached octet. So in order to do that, we need to move the lone pair to here. We'll move one lone pair there, we move one lone pair there. Hence, we can make it into this 0, double bond N, double bond N. Right? So this one is gone. You don't have to take this one anymore. So there's going to be 2. There's going to be 4 lone pair here, and another lone pair here. Hence, getting this question. We're getting this first Lewis structure. Okay, so the second one. How do I get the second one? Well, since we can move, you can see the lone pair. We can move the lone pair over here to make it, and then we can move one lone pair here back to its place. So when we move it, it's going to be 0, triple bond N, 1 single bond N. Since this one is already moved, so we don't have to take that one. So it's going to be 1 lone pair here, and then this one, since it's already moved to there, so it's going to be 6 here. 1, 2, 3, 4, 5, 6. Hence, getting the structure for number 2. The number 3 is also the same thing. Okay, so number 3, we can okay, so this Lewis structure number 3. We can move 1 over here, we have 1 of the lone pair here, and we can move 1 lone pair back to here. Hence, when you do this, it becomes 0, a single bond N, and by triple bond N. And since we already moved 1 here, there's going to be 6 here, and then since this one is already moved here, there's going to be 1 there. Hence, making the question for this one. Okay, so once you get that figured out, you can see that all of these are already in stable octet. 2468, 2468, 2468. For oxygen, 2468. For the nitrogen, 2468, 2468. So all of these is octet, and also for the Lewis structure number 3. 2468, 2468, and 2468. So that means all of this is the possible structures for gas nitride oxide. Moving to the next question, it says to assign the formal charge assign the formal charge for each atom in the resonance structure. It says assign the formal charges, so that means you don't need to show the calculation. But if it does show the calculation, basically what you gotta do here is to calculate the formal charge, which is Fc. Formal charge is equals to the number of valence electron minus the number of bonding pair. Bonding pair is the lines, by the way. These lines are called the bonding pair, and the dots here is called the lone pair. Bonding pair minus the lone pair. Okay, so for example, we're going to take the question for this one, the Lewis structure number 1. So oxygen has 6 valence electron minus 2 lines there, the bonding pair, minus lone pair 1, 2, 3, 4, so 4 lone pairs, hence making the formal charge for oxygen is 0. The same here, and basically it's all the same for all of this one. For example, you want to calculate for the nitrogen, right? Okay, for specifically this nitrogen. Okay, so nitrogen has 5 valence electron, minus by, there's 4 lines, so minus 4. As you can see here, there's no lone pairs here, so minus 0. So 5 minus 4 is plus 1, hence making the formal charge is 1. And basically that's what you do for all of the possible Lewis structure. Alright, moving on to the next question. Which is the most plausible Lewis structure? So there are a couple of factors that can help you to determine which one is the most plausible Lewis structure, which is the formal charge should be approaching 0. Formal charge should be approaching 0, or the most smallest possible value. But as you can see here, all of them when added up is equals to 0. So 0 plus 1 plus negative 1 is equals to 0. Plus 1 plus 1 plus negative 2 is also equal to 0. Negative 1 plus positive 1 plus 0 is also equal to 0. So how are we going to determine the most plausible? Well, we go and look for the second factor, which is determined by the electronegativity of the atom. Electronegativity of the atom. So what I mean by this is that if you can see here that between nitrogen and oxygen, you should know that oxygen is more electronegative. Hence, when it is more electronegative, it should have the negative value, for example, than the SK015. As you can see here, the Lewis structure for the first one, the oxygen in the first Lewis structure has 0 value, has 0 formal charge. That means it's not, so it's wrong. But the second one has a positive formal charge. We are looking for a negative because O is more electronegative than N. Hence, Lewis structure for oxygen in Lewis structure number 3 is the correct one. That means the most plausible Lewis structure should be structure 3. So this is the reason. So which is the most plausible structure is structure 3, which is O, single bond N, and triple bond N. It is the most plausible structure because it has the smallest formal charge. Because it has the smallest formal charge atoms. And since O is more electronegative than N, O should carry a negative formal charge. Alright, moving on to the next question, question B. So, NF3 molecule is used. NF3 is used for etching in a semiconductor fabrication process. B1 is draw the Lewis structure of NF3. So, as I said earlier, in order to determine the Lewis structure, it is first to calculate the total valence electron. So, nitrogen has 5 valence electron and has 1 here. So 5 times 1 is 5. And fluorine has 7 valence electron. And from the molecule we know it has 3. So 7 times 3 is 21. So 5 plus 21 is 26. Hence first you draw. So there's going to be 3 here, right? So 26 here. So this one is going to be total 26. So we have 3 lines here. So 3 lines, one represent 2 electrons. So 3 times 2 is 6. So 26 minus 6 is 20. So that means it's going to be 20. So you have to fill in all of this. So 1, 2. Next, we have to fill in the electrons. 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so from here, we know that 6, there's going to be 6, 12, 86 times 6 times 6 is 18. So 20 minus 18 is 2. So there's going to be 2 extra, and this extra should be the lone pair on the central atom. So okay, and that is the Lewis structure for NF3. As you can see, like how I draw over here. Second is state is molecular geometry. Since it says state, that means you have to put in all of the required information. So first you need to determine the class. How to determine the class is by looking at the Lewis structure. As you can see here, there's okay, so A represents A represents the central atom, and B represents the the terminals, and E represents the lone pair of electron. So as you can see here, there's 1 A, so A. There's 3 B's, so A, B, 3. So there's 3 B's, 1, 2, 3, so 3 B's, so A, B, 3. And there's 1 lone pair, as you can see here, so A, B, 3E. So the class should be A, B, 3E. And A, B, 3E, so you have to draw the sheet for A, B, 3E. This one, there's no way of remembering it. You just have to memorize what the shape for each one. But basically, for AB3E, you should get this is a tetrahedral. So the electron pair arrangement is tetrahedral. The bond angle is less than 109.5, and the molecular shape is trigonal pyramidal. Okay, so moving on to the next question, which is question number 3. State the type of hybrid. To determine the type of hybrid, you must first look at the center atom. From the of course, you need to prove to the Lewis structure. Okay, so from this Lewis structure, you can see that the center atom is the nitrogen. So from the nitrogen, you can see there's just 1, 2, 3, 4 types of bond there. So that means if this type of bond is 4, then it should be sp3. So because there's 1 S and 3 P, so 1 S and 3 P, there's 1, 2, 3, 4, 1, 2, 3, 4, hence making it sp3. Do the next one. Determine the polarity of the molecule and the reason. So to determine the molecule, the polarity of the molecule, you need to draw the molecular shape of the molecule. So for NF3, just like the above, and then need to determine which one is more electronegative. So as you all know, F is more electronegative than N. Hence, when it's more electronegative, there's going to be the charge distribution is going to be uneven because F is more electronegative. It's going to be pulled towards there. basically N is going to go towards there because it's going to be pulled towards there. It's going to also be pulled to here and also pulled towards there. Hence, when this happens, the polar molecule, the dipole moment does not equal to 0 because it's moving towards downwards. It's going to go towards, it's go downwards, and the dipole moment does not equal to 0. So this is how I explained it. NF3 is a polar molecule because fluorine is more electronegative than nitrogen and leads to undistribution of charge. The dipole moments does not cancel each other out due to asymmetrical shape, as you can see there. One pulled over there, one pulled over there, and one is pulled over there in different directions, making it go downwards. Hence, the dipole moment does not equal to 0. Okay, so question C. Aluminium. Aluminium and magnesium are metals. Okay. Question number 1. Explain the formation of metallic bonds in magnesium using the electron C model. So, since it says using the electron C model, it's a must that we draw the electron C model and label it electron C model of Mg. This is a must because it says using the electron C model, so you have to draw it. So this is how to draw the metallic electron C model is like this, as you can see here. The minimum to draw, how many mg's to draw here inside, how many atoms you want to draw inside, is the minimum is 6. Then needs to be at least 6 in the box. Alright, so Mg2 plus. Since the valency electron is freely moving, this is delocalized sea of electrons, you can put it randomly but near the ion. So Mg2 plus, it releases 2 electrons, so 2 electrons there, 2 electrons there, just like so. And so this is the explanation. Each magnesium atom releases 2 electrons and forms Mg2 plus ions. Alright, so just like I said earlier, the Mg releases 2 electrons. As you can see there, that's why there's two electrons around it. The positive Mg2 plus is surrounded by C nucleus of valence electron, just like I said earlier. The electrostatic forces with Mg2 plus and ion and the C of the nucleus electron is called the metallic bond. That is how you explain it. So moving on to the second question. Why aluminium has a higher boiling point than magnesium? Alright. So to determine the boiling point, you must first know that how many valence electron a certain atom releases. As you know, aluminium releases 3 Al3 plus, right? So that means it releases 3 valence electron. And magnesium it releases magnesium releases Mg2 plus, that means it releases 2 valence electron. Alright, so that means the higher it has so that means just like I said, aluminium releases 3 valence electron and magnesium 2 valence electrons. That means, hence, the valence electron is directly proportional to the strength of electric forces. So when there's more electron, there's going to be a stronger electrostatic force. So that means aluminium has a stronger electrostatic force than magnesium. So when there's more electrostatic force, it needs more energy, right? So it needs more energy to required to break the bond. Thus, aluminium has a higher boiling point than magnesium. So basically, the more an atom releases an electron, the higher the stronger the electrostatic force. Hence, when the electrostatic force increases, there are more energy required to break the certain bond. Hence, the boiling point will become stronger. The boiling point will increase. So that is it for this question, which is set B 2022 and 2023. Thanks for watching.